Hello and welcome to this lecture on analysis of variance, usually abbreviated and referred to as ANOVA. My name is Brian Miller. I'll be guiding you through this tutorial, so let's get started. ANOVA. In ANOVA, or analysis of variance, we're simply comparing the means of two or more groups on some particular instrument, measure, scale, variable, whatever it is you want to call it. The dependent variable, the thing being measured, must be continuous. The independent variable must be nominal or ordinal, but it is, of course, categorical. So you need a categorical variable with at least two independent groups. For example, you could use different nationalities, you could do different grade levels in school for second, third graders, etc. And this would be the independent variable. And the continuous variable measured on an interval or a ratio scale would be the dependent variable. So, for example, you could use the IQ score, and that's measured continuously from about 40 to about 300, but most people are at 100, okay? So ANOVA with only two groups is the exact same thing as a t-test. So that's some interesting little conversation fodder for your next cocktail party. Did you know that the analysis of variance with two groups is exactly the same thing as a t-test? After they kick you out of the party, you can be proud of yourself for what you know about statistics. Let's move on. So let's compare t-test to ANOVA. So a t-test compares the means of only two groups, just two. You cannot run a t-test on more than two groups. The two groups can be independent samples. They can be the same sample measured twice, or it can be one group compared to some score that you've dreamt up as a single group t-test, and that score you've dreamt up could be something that you're comparing it to, but nevertheless that's a proxy for a score in another group, all people not in the group being tested. Each t-test has a chance of being wrong, and we refer to this as a type 1 error. So a type 1 error is finding some effect where there actually really is not one, that is, finding a significant effect in the sample, and there is not really a significant difference in the population. You can think of type 1 error as convicting an innocent person in a court of law. You have found them guilty when they're not really guilty. The more tests you do on the data, the greater the chances of being wrong are. So the way to overcome this, rather than simply conducting a bunch of t-tests on a sample with three or more groups, is to run an ANOVA. So ANOVA tests more than two groups, and this helps provide some certainty in concluding whether or not there is a significant difference. It essentially seeks the average distance between the means of multiple groups using the squared value of the difference between the means. That squared value of the difference between the means is important. It is squared because some groups will be less than and thus have a negative value, and some groups will be larger than and have a positive value. Therefore, by squaring the differences, everything is on the same metric, and the perception that a negative value is less than a positive value is moot. Let's move on. Here's a visual display of a difference in group means. Essentially, we're trying to find out, is there a non-zero difference between these groups in the population? And so we have the red group, normally distributed, with an X bar sub 1 of about 7. And we have the green group with the X bar sub 2 of about 13. And we have the blue group with an X bar sub 3 of about 17. The question is there a difference amongst these samples that we can generalize to the population? A little bit more clearly, more technically, is there a difference in the population between members of these three groups? Let's move on. So simply conducting a series of multiple t-tests are not appropriate. Multiple t-tests have this inflated experiment-wise or family-wise, it's sometimes referred to, probability of type 1 error. So if we set our alpha value at 0.05, alpha being the proverbial p less than 0.05, then we have a 1 in 20 chance of making a type 1 error. That's 5%, right? Now, if we run t-test after t-test after t-test, let's say we have 13 or 14 groups, we're going to have over 100 pairwise t-tests. The chance of finding something significant in there is pretty doggone good. In fact, of over 100, we'll probably find 5 pairs that are statistically significantly different from each other, even if the data is completely random. So we want to make sure that we minimize the experiment-wise probability of type 1 error. Again, with 100 tests, 5 of them on random data are likely to show statistical significance. So if all the tests are independent, then we have something called alpha experiment-wise. So we can calculate the p-value below which a test needs to be found to be statistically significant. Actually, the test score goes up and the probability of type 1 error goes down. So alpha experiment-wise is equal to 1 minus the difference between 1 and alpha to the power of c, where c is the number of null hypotheses being tested. So for example, let's say we have 6 different tests here in the effects of Prozac versus Elavil versus Zoloft versus Tofranil. So we have 4 different types of antidepressants, and we want to find out which of them is most effective in treating depression. That is, which, after taking these prescriptions for a while, which sample using a particular prescription results in the lowest depression. That is, which of these drugs is most effective. Well, with 4 different drugs, we have 6 different tests. So 1 minus, open parentheses, 1 minus 0.06, close parentheses, to the power of 6 is equal to 0.265. So because 6 tests are not generally completely independent, then we know that alpha is greater than 0.05 and less than 0.265, and the exact alpha is difficult to assess, and oh my gosh, you probably are lost now. Hang in there. What we're saying is we can run an ANOVA and just not worry about all of these experiment-wise family errors and calculations like that. It's a whole lot simpler than you think. Let's move on. So we have hypotheses with 3 or more samples. So this is the null hypothesis that mu sub 1, that's the population mean, mu sub 1 is equal to mu sub 2 is equal to mu sub 3 is equal to mu sub 4. Okay, that's technically what we're testing. Are these things the same thing? Alternatively, we tend to phrase them a little bit more differently. So this implies that mu sub 1 is not equal to mu sub 2 is not equal to mu sub 3, and mu sub 3 is not equal to mu sub 4. But in reality, there are 6 different pairs. And we would reject the null if any one of the pairwise expressions is true. For example, if we find that mu sub 1 is not equal to mu sub 2, then we're going to technically not accept the alternative hypothesis, but we'll reject the null. Thus, when we reject this omnibus null, we assert that at least one of the pairwise nulls is not true. That is, we will find an overall statistically significant difference somewhere in the all possible pairs of combinations. Somewhere in there, there's a difference. To find the difference, we would do post hoc paired comparisons, which we'll discuss in a little while. In the meantime, let's move on. So how does ANOVA actually work? The question is between group variation larger than within group variation? Is the distance between the means of the groups larger than the average distance within the groups? Ideally, we would hope so. So here's the answer. Calculate the average amount of variation within each sample. This is called the mean square within, or the mean square error. And this is essentially the same as the standard error that we used in the t-test. So the average amount of variation within each sample. Then we have to find the average amount of variation between the group means. This is called mean square between. Remember, it's squared because some values are less and some values are larger than. And so in order to put them on the same metric, we just square them so that less than values become positive. The square of two negative values is positive. Okay, so this is called the mean square between. And this is essentially the same as the numerator in an independent samples t-test. So you should be seeing a little similarity between the t-test and the ANOVA. The third step, you have to find the ratio by dividing the mean square between by the mean square error. This is what provides the F-score, the F-test, the F-value. This is our old formula of dividing the statistic of interest, that is the average distance between the group means, by its standard error. The standard error goes in the denominator in all sorts of statistical tests. The fourth step, when we have our F value, we can look up our family of F distributions to see if the differences between the groups are statistically significant. Again, we're trying to find out if the distance between the group means is larger than the average distance within the groups. Let's move on. All right, if the null hypothesis is true, then the two variances, variance between, variance within, will be equal. And F will be 1. And here's the formula. The between group point estimate of, this is a lowercase sigma, sigma squared is the variance in the population. The between group point estimate of sigma squared divided by the within group point estimate of sigma squared. We want F-scores to be larger. We want more mean squares between than we have mean squares within. We want the distance from the means to be larger than the distance within the groups. Let's move on. Okay, this figure shows the F distribution for varying levels of degrees of freedom. As you can see, the more groups one has, the smaller the critical value is needed to reject the null. Let's take a look at this. So look at this gray curve here. This has degrees of freedom 2 and sample size of 20. So it's 2 and 20, essentially it's 20 sample size. There is some difference there. Anyway, with 2 and 20 degrees of freedom, the F distribution looks like this. Now let's look at the black curve. Here, this one is for degrees of freedom 1 and 20. All right, so with only 1 degree of freedom, it's a much flatter area. Now the dark blue is differently shaped as well. The light blue is differently shaped as well. There is a family of F distributions. What we want to find is an F score which is large enough that it's in the tail beyond the critical value. So here the critical value with degrees of freedom 8 and 20 is 2.45. The degrees of freedom with 4 and 20 is 2.87. So an F value larger than 2.87 down in the tail is statistically significant. Thankfully, we don't really have to look at F-score tables anymore. They're really complicated because you have 2 different degrees of freedom. Let's move on. Post hoc paired comparisons. Now, ANOVA will only find if there is some difference, any difference that exists between 3 or more groups. If there is some difference between group 1 and 2, maybe group 1 and 3, maybe it's group 1 and 8. If there is some statistically significant difference there, then it will arise. Now, if and only if the significant F score, then you'll need to identify where the difference is. So if it results in a significant F score, you simply know that somewhere in your multiple groups, you have a pair that are different. somewhere. Now, we want to find out where that pair is. So once again, we have to correct for type 1 error because now we're looking at all possible pairwise comparisons. And if there's 4 different groups, then there are 6 pairwise comparisons. Now, there are a host of different built-in corrections. For example, the classic one is the Bonferroni. The Bonferroni correction is you simply divide your significance level, it's typically 0.05, by the number of tests, so you divide it by 6. The Chaffee test is a little bit different, and then there's Tukey's HSD, which stands for, believe it or not, honestly significant difference. These things are built into most software programs. You don't have to worry about how to calculate them. What you do need to know is that these 3 different tests, post hoc paired comparison test, automatically correct for the propensity for type 1 error. Let's move on. Well, thanks. That's all for now.